Hello, everyone. Welcome back. This is section 4.7, optimization problems. All along, we have seen a lot of information about the graph, how to find absolute maximum, minimum, local max, local minimum, and then where the graph is increasing, where the graph is decreasing, how to find where the intervals are, what the intervals are when the graph is concave upward, downward, inflection points. So much about the graphs. So the purpose of all of this is also to see the real world application problems, one of which is optimization problem. Anything that we do, we want to optimize the outcome. So if we want to travel the shortest route possible, we want to minimize the time, we want to minimize the cost, maximize the profit. So optimization occurs in many real world situations. So in this section, the methods that we have learned in this chapter for finding extreme values have practical applications. If you own a business, you would like to minimize the cost and maximize the profit. When traveling, you want to minimize the transportation time. Steps in solving optimization problems. First, you understand the problem, then you draw a diagram, introduce the notation. Suppose we want to maximize or minimize the quantity, call it Q, and select symbols A, B, C, etc. for other unknown quantities. The function that we want to maximize or minimize is usually called the objective function. If Q is being expressed as a function of more than one variable, in step 4, find the relationships in the form of equations among variables. Use equations to eliminate all but one of the variables in the expression for Q. By the given relation, suppose the objective function that you want to minimize has more than one variable, and by the given conditions in the problem, you try to minimize the number of variables in the objective function. Use methods in 4.1 and 4.3 to find the absolute maximum or minimum value of f. If f is a closed interval, then use the closed interval method to find the absolute max and absolute minimum. The first derivative test for absolute extreme values. Suppose that c is a critical number of a continuous function defined on an interval. Then if f prime x is more than 0 for all x less than c, and f prime x is less than 0 for all x less than c, so that means the graph is increasing and then decreasing. So f of c is the absolute maximum. It's called the absolute maximum. If f prime x is, let's say in this scenario, f prime x is more than 0 to the left of c, and f prime c is less than 0 to the right of c. And if the graph was like this, then to the left of c, f prime x is less than 0, decreasing. To the right of c, the graph is increasing. Then that will be so this will be a max, and this will be the min. So if f prime x is less than 0 for all x less than c, and f prime x is more than 0 for all x greater than c, and it is this scenario, then f of c is the absolute minimum. All right. There are some suggested problems of this section. Here, this problem, practice test number 8, 18, practice final 19, practice final 25 are all done in the section videos. Please check them out. This is the problem, practice test 8, practice test 18, practice final 19, and practice test and practice final 25. All these problems are there in the section videos. Now, for this section, for the example, we'll try to do one of the first two problems. We can pick number 7 to do here in this video. Find the dimensions of a rectangle with perimeter 100 meters and whose area is as large as possible. Find the dimensions of a rectangle with perimeter. Perimeter is given and whose area is as large as possible. This is problem number 7. So we are given a rectangle here. So rectangle has a perimeter, given perimeter. So let's call the length as x. We'll call the length as width as y. This is the length and this is the width. So it is measured in, the dimensions are given in terms of meters. So perimeter is given in terms of meters. So what is the perimeter of a rectangle? P equal to 2x plus 2y. This is given to be, the value is given here, which is equal to 100 meters. This 100 meters. So let's call 2x plus 2y equal to 100, which is given. If you reduce it or divide everything by 2, you get x plus y equal to 50. We'll call it equation 1. So length plus y equal to 50. So what is y equal to? So it is 50 minus x. And definitely x has to be smaller than 50 because x and y are positive quantities. So this x cannot exceed 50. So this clearly tells us that x should be smaller than 50. If it is above 50, what happens to y? Y becomes negative. Y is the width of the rectangle, so it cannot be a negative value. So it is the upper value of x can only be 50. So from the given relation, from equation 1, we have solved for y. Now, what is the objective function? What is that function we want to maximize or minimize, which is in this case, the area function. Area of the rectangle is x times y. This is the one we want to maximize because the problem tells us find the dimensions of a rectangle. Dimensions means find the length and width. The dimensions actually means the length and width. Whose area is as large as possible. So that is the objective function. So x times, from what we have learned here in 2, we can substitute 50 minus x. That is the area function. Even though it involved 2 variables initially, we reduced it to 1 variable using the relation y equal to 50 minus x. Now, area function is no longer a 2 variable function. It has got only 1 variable, which is x. And this is the objective function, and this is the one that we want to maximize. So call it equation 3. So in order to maximize or minimize any function, what is the step that we do? Find the critical number, right? Find the critical number. So how do you find the critical number? By taking the derivative and setting it to 0. A of x, if you distribute, it becomes 50x minus x squared, right? Area of x becomes, if you distribute the x, it becomes 50x minus x squared. Now you are taking the derivative of that, which is 50 minus 2x. We'll set that to 0. So 2x equal to 50 or x equal to 25. So x is the length in this case, so x equal to 25. Then, so in this case, what we can do, let's take the critical number here, and we have to see what happens to the left side of 25 or right side of 25. If it to the left side of 25, which is nothing but precisely the first derivative test. So that is the one we are going to use. So to the left of 25, then a prime x, when x is less than 25, we can give a value here. So let's say test point equal to, say 10, x equal to 10. And then here to the right of 25, the whole thing can be only 0 to 50, right? So because we have said that domain of x is only from 0 to 50. So we can take a test point to the left of 25 and to the right of 25. And then we'll find out what the sign of a prime x is. So it is 50 minus, when x equal to 10, a prime x equal to 50 minus 2 times 10. So it is 50 minus 20, which is equal to 30. So a prime x is more than 0 in the interval 0 to 25. So which is an increasing function. Same way, when x equal to 30, when x equal to 30, a prime x equal to 50 minus 2 times 30, which is 50 minus 60, which is negative 10. So a prime x is negative. So what does these two conditions say? A prime x is increasing. So a prime a of x is decreasing on the interval 25 to 50. Right? So what does that mean? To the left of 25, it is increasing. To the right of 25, it is decreasing. So if you consider 25 as a critical point, so it is increasing to the left of 25 and decreasing to the right of 25. Increase, and this is decrease. So that will be a peak. So by first derivative test, a of x has a max at x equal to 25. Pretty much this proves that the function has, the objective function is maximized. A of x, which is the area, is maximized at x equal to 25. So if x was 25, what is y equal to? Which is 50 minus 2 times x. So 50 minus 2 times 50, a of y equal to 50 minus x. 50 minus x. So it is 50 minus x here, which is 50 minus 25, which is equal to 25 also. So x is 25, y is also 25. So the dimensions that make dimensions of the rectangle to give the maximum area. Length equal to 25 meters because the dimensions are given in terms of meters. Width equal to 25 meters as well. This is 1. So what dimensions will make the area maximum? The length and width being equal to 25 meters, which means the rectangle is a square. So here in this problem, we did first derivative test to show that there is a maximum. We can also use second derivative test here. So if you consider a prime x, we found that to be equal to 50 minus 2x. So what is a double prime x? So which will be 50 minus, which is just negative 2. What is the derivative of 50 minus 2x? Which is just negative 2. This tells us that the second derivative is less than 0, no matter what the value of x is. So that means it is the graph of a of x is concave down. So we found that the critical point, so at the critical point, at the critical number is x equal to 25. And at the critical number, the second derivative is negative. So by second derivative test, there is a maximum at x equal to 25. Right? So for the same problem, you could have also used the second derivative test to justify that the objective function is maximized. So in the second method, so instead of using first derivative test, we can also use second derivative test. Hope this video helps. Please remember to watch the harder problems in this section, practice test 8, 18, 19, 25. So you'll get a better idea of optimization problems. Hope this video helps and watch my next video on 4.8.